So, algebraic fractions and using them to solve equations. Okay, now, the key thing to remember before we do anything in terms of solving equations using algebraic fractions is to understand the concept of an equation, because this can be a bit tricky and is where mistakes tend to be made. So, remember that an equation, okay, is two sets of expressions in equality. So one set of expressions, okay, equals another set of expressions. Okay, and the reason I say set is because you can link these all together with brackets and additions and subtractions and all sorts of things. But ultimately, what's on one side, if you evaluate it, must equal what's on the other side. Now, a lot of you have been taught a little mantra which goes by the song of what you do to one side, you do to the other side. And that is true, but you need to understand what it actually means, because it's very easy to make a mistake. So, let's consider the concept of balance. Okay, so an expression, this is an identity. We're not going to use an equation because we're not going to try and solve it. So we're going to, it's a stated constant identity, okay? 5 plus 3, 3 equals 8. It's always equal to 8, or 8 is always equal to 5 plus 3. Now, the concept of balance tells us that whatever we do to one side, we have to do to the other side. But here we have two things on one side and one thing on the other side. And where people make mistakes is they think you only have to do something to one element of what's on one side, one term, but you have to do it to all the terms on one side. So effectively what you do is you have to consider it like that. When you're applying a balance operation, you're doing it to everything, so everything goes in the brackets, and then they become an inviolable. So, for instance, here's 5 plus 3, okay, and I'm going to add 1 to it. So we're going to add 1 to both sides, okay? Now, to do that, I do this. Okay, is that true? So 5 plus 3 plus 1 is 9. Does 9 always equal 9? Yes, it does. So we know that's true. Similarly, take away. Subtract 5 plus 3, take away 1. 3 equals 8, take away 1. Is it true that 7 always equals 7? Yes, it is. Okay, so you can see what we've done there. Now, in this case, it doesn't matter whether you treat it as an inviolable single term, so the brackets around it. Where it does is with multiplication and division, okay? Because I've seen lots of examples where students will multiply or divide one term when there may be more than one term on the other side. So let's have a look. If we're going to times this by 2. Now, we have 5 plus 3, and we times that by 2. Okay. Is that the same as 8 times by 2? So, does 5 plus 3 is 8 times 2 is 16. Is 16 identical to 16? Yes, it is. All right. Now, you're probably thinking, why is he teaching us the obvious here? Okay. So, let's have a look at division as well. Oops, division by 2. Okay, so 5 plus 3 divided by 2. Is that equal to 8 divided by 2? So, essentially, is 5 plus 3 is 8 divided by 2 is 4 always equal to 4? Yes, it is. And again, why am I teaching this? Well, I'm teaching this because when we get to using algebraic fractions, what we can end up with is something like this. We can end up with 5 plus 3, okay? And we can say, right, I am going to divide my 8 by 2. So I'm going to make it a half. Now, what you have to make sure you do is you divide the whole thing by 2, okay? Now, where this becomes weird, especially when you've got unknowns or letters in it, is some people don't realise that that is the same as that. Okay. So here we have a common denominator because each of the elements, or each of the terms, has to be acted upon, no matter how many are on one side or on the other side. Okay, so be careful with that. So, for instance, the reason I'm giving you this is because, and here's an example, if I can remember one, x divided by 2 plus 3 equals 8. Now people will go, right, I'm going to times this side by 2, because there's an x is 2, and I'm going to side that side by 2. And they'll go, right, so x over 2 times that gives me my x plus 3 equals 16. Then I'll go x equals 16 take away 3 is 13. There's my answer. Except when you put 13 back, 13 divided by 2 plus 3 doesn't equal 8. And the reason is because when they multiply by 2, you have to do it to everything on the same side, or everything on both sides. So yes, they times this by 2, and they times that by 2, but that's because they thought you times both sides by 2. They forgot about the plus 3. Okay, so if we correct that, okay, that becomes 6. Yeah, so then our correction is x equals 16 take away 6, so x equals 10. Does that work? Well, 10 divided by 2 is 5, 5 plus 3 is 8. So that's why, okay? Yeah, you're getting taught to suck eggs there, but you need to understand the concept of balance across an equation, okay? To solve an equation then, we're trying to find the value or values of x which make the equation valid or true. So substitute a number in for x, calculate what's on the left-hand side, does it equal what's on the right-hand side? And if it does, then that x is a solution. Now, in the previous slide, we talked about one way of thinking about this is unwrapping what's been done to x. Now, an example of how to consider that is to think about, okay, let's write this out again. Okay, so what's been done to x? Well, the first thing that's been done is it's been times by 3. So we'll stick that there. What's the next thing that's being done? Well, once it's been times by 3, we're adding 4 to it. So there's a bracket there. And what's being done to that? Well, once we've times it by 3 and added 4 to it, we're dividing by 7. And if you look at those brackets represent a journey outwards, if you like, from x. So to solve them, we go backwards. We take the outer layer and we peel it off first. So we could argue that the outer layer, okay, I'll put it over here, that is the divide by 7. That's the outer one. Then the next one is the blue one. The blue one is where we're adding 4. Let's do that. And then the inner one is where we're timesing by 3. Okay, so to solve this, we have to go from the outer to the inner, doing the inverse. So the inverse is times by 7, take away 4, divide by 3. Okay, so that's one way to look at this. So in this case, the first thing we're going to do, if we start, we're going to times by 7. Okay, so if we times by 7, let's do all in red now. So 3x plus 4 over 7 equals 4. First thing we've said is we're going to times by 7, which is this thing. So times by 7. So we times, now remember that's all in a bracket, so timesing that side by 7 just gives us 3x plus 4. 4 times 7 is 28. Next thing, take away 4. So if we take away 4, we get 3x equals 28. Take away 4 is 24. And then the next thing, final thing, we divide by 3. And that gives us x equals 8. Okay, just check to see if that's the answer. If you stick it in here, is 3 times 8 plus 4 divided by 7 equal to 4. Well, 3/8 is 24, plus 4 is 28. 28 divided by 7 is 4. Yes, it is. So here we have two simple examples, okay, of an equation. We know it's an equation because it has an equal sign and one type of letter, okay? So if it had an x and an x squared, they're still the same type of letter, so they'd be an equation. Whereas if they had an x and a y, they wouldn't be an equation, they'd be a formula, all right? Because you can only solve something that has only one letter, okay? So first one, let's have a look. So we've got 2x, it's being divided by 6, and it equals 7. The result equals 7, okay? Now, one way to think about equations is, talk about an onion, peeling it backwards. Look at what's being done to the x, because ultimately, at the bottom of your working, you want x equals a number. So you can think about it in terms of what you have to do to unpack or unwrap the x. So it's being times by 2, and then it's being divided by 6. So to unpack it, we do the opposite or the inverse. So the last thing we said is it's being divided by 6. So the first thing we're going to do is times both sides by 6. Okay, so times both sides by 6. Use a square bracket to indicate a note rather than a curvy bracket to indicate an operator. So if we times the left-hand side by 6, we get 2x. And if we times the right-hand side by 6, 6 sevens are 42. Okay, now what's being done to the x? Well, it's just being times by 2, so we do the inverse of that. We divide by 2, we have to divide both sides to keep balance. So 2x divided by 2 is x, 42 divided by 2 is 21. Always check. One of the nice things about equations, one of the few times you can do it in maths, is you can check. You can take the 21 and you can put it back in here. So is 2 times 21 divided by 6 equal to 7. Well, 2 21s are 42. 42 divided by 6 is 7. Yes, so you know that this is correct. Okay. Now, I've given this one as an example because I want to show you two ways you can do it. Now, we have two terms on one side, the left-hand side, and a term on the right-hand side. And if we could use the system we talked about before, what's being done to the x? Well, you're timesing it by 3, you're dividing it, the result by 4, and you're adding 1 to that result, and it should come to 4. So, ideally, if you'd use method 1, okay, we were adding 1 is the last thing we did, so we're going to take 1 away. So, if we have 3x over 4 plus 1 equals 4, and we take away 1, we end up with 3x over 4 on this side. 4 take away 1 is 3 on that side. What's been done to the x? Well, we're timesing it by 3 and dividing it by 4. So we can undo the division by 4, because that's the last thing we said. So divide by 4. Oops. Not divide by 4, times by 4, because we're undoing a division by 4. So 3x over 4 times 4 is 3x. 3 times 4 is 12. What's been done to the x? Well, we're timesing it by 3. Do the opposite, the inverse, divide by 3. So we have x equal 12 divided by 3 is 4. Does it work? Well, let's have a look. So is 3 times 4 over 4 plus 1 equal to 4. 3 4s are 12. Divided by 4 is 3. 3 plus 1 is 4. Yes, so we know we're right. Now, I want to show you the other way. Now, in this case, you wouldn't do it, although I've seen people make mistakes here, okay? But it's going to prove the point I went on about in the last slide, and that you will have to consider more complicated equations. So, we have 3x over 4 plus 1 equals 4. Now, the x is being times by 3, and the result is being divided by 4. So, we want to remove that division by 4, which we do as the inverse, so we times both sides by 4. Okay? Now, you're timesing both sides, and that means everything on both sides. Okay? So, we times the first thing by 4, we get 3x. We times the second thing by 4. So 1 times 4 is 4. And then we times the 4 on the right-hand side by 4. So it's 16. Okay, so all three terms have been times by 4. So it's still in balance. Then we have a look at it. Well, 3x, we've got 3x, we're adding 4 to it, so we take the 4 away. So 3x equals 16 take away 4 is 12. 3x, so 3 times x, opposite of 3 times the inverse is divided by 3. So x equals 4. Okay, so 2 different methods of getting to it. You're getting to the right solution. So the first method was easy in that we just moved the 1 across, okay? We took a +1 and we made it into a -1. Whereas the second solution, we applied a modifier operation, the times by 4 to all 3 terms. Most of the time, you're going to want to do the first method, but there are times when you have much more complicated fractions where the second method is an easier method to use. Okay, so just 2 more arrows in your bow of math destruction. Sometimes with equations, you'll be presented with them in a manner that seems to be the wrong way around. But remember, there is no wrong way around in algebra. Okay, you can do it this direction or in this form, or you can reflect it. So remember, a reflection is literally flipping it across or through the equal sign. Okay, you're not moving things around, although you can, you're just reflecting it. So that is identical to that. So if you want to do that, feel free, but we'll go with this one. Okay, so let's do what we did last time. So x is being times by 4. The result of that is having 6 taken away, and the result of that is being divided by 2. So we're going to do the inverse of it, working backwards. So the first thing we want to do is get rid of this denominator, which is a division by 2. So we're going to times by 2. So let's see, 5 equals 4x, subtract 6 over 2, and we are going to times by 2 both sides. Remember, this is a single thing, so times that by 2 just gets rid of the denominator, or gives you a denominator of 1, times the other side by 2, so 10 equals 4x, take 6. We're adding 6 to the result of 4 times x, so we do the opposite of take away 6, which is add 6. So that's 16 equals 4x. We don't want 4 times x, we just want 1x, so we are going to divide both sides by 4. So 4 equals x, or reflect it round, x equals 4. Just test it, does it work? So is 5 equal to 4 times our x value, which is 4, take away 6, divided by 2. Well, 4 times 4 is 16. 16 take away 6 is 10. 10 divided by 2 is 5. Yes. So here we've got a little bit of a step up. And the reason for that is that the x is now on the bottom, or part of one or more of the denominators. Again, though, it's exactly the same rules. Don't freak out. Don't pull your hair out. It's nice and easy. Now, one thing to remember is the simplest thing to help us is to do this, because the x plus 3 is inviolable, okay? You consider it as one entity because it is dividing 3. So we're going to consider it in that form. Now, this is where we can use this. A over B equals C over D, okay? If you have something in that format, you can rearrange it into, make it exactly equal to this. AD equals BC. Okay, and that's what we call cross multiplying, because if you notice, what's happening is that's going up there and that's going there. The long reason for this is that if you consider you've got A over B equals C over D. Okay, so first thing you want to do is you want to get rid of this denominator. So to get rid of a divide by B, you times both sides by B. Similarly, here, to get rid of this denominator, dividing by D, you times both sides by D. So what we're actually doing is this. We're actually going AB times B times D equals C over D times B times D. Okay, and in this case, the D's cancel out, which leaves you with BC, And here, the b's cancel out, leaving you with AD. Okay, so that's the longhand. But once you understand the longhand, you can just refer to it as cross-multiplying. And either of these forms can be transferred into their opposite. Okay, so in this, we can cross-multiply. So we can go 2x plus 3 equals 3x. Multiply out 2x plus 6 equals 3x. We're going to move the smaller x. That's the smaller x. So now I'm going to talk about moving across an equal sign. Now some mathematicians hate this concept because it's not exactly what it means. But if you were going to move that, if you didn't want to get rid of that 2x from the left-hand side, you have to take 2x away. So you're taking 2x away from the other side. But that is the equivalent of moving this on here and changing its sign. Gives you negative 2x. Okay? But by talking about moving things across equal signs, it gives you a better idea of the flow of an algebraic manipulation. So yeah, 6 equals x, reflect it, x equals 6. Let's try it. Does it work? Well, let's see. Let's use blue. So is 2 over 6 equal to 3 over 6 plus 3? Well, 2 over 6 is a third. 3 and 6 over 3 is, that's 3 over 9. And 3 over 9 is a third. So yes. So we know that that's right. Now, cross-multiply is a really powerful tool if you can find this form, okay? The A over B equals C over D. Now, you'll find that in all sorts of places. Trigonometry, specifically. The sine rule or the standard trigonometric functions. So, you know, sine x equals opposite over hypotenuse. If you think about that as being over 1, then you've got A over B equals C over D. You can cross multiply. So it is really powerful. So keep an eye on it. Okay, another one. We could recognise that this itself is a form of A over B equals C over D. All we'd have to do is put the 1 there. Okay? So even though this numerator here is a bracket being multiplied out, it still can be considered as one inviolable term, can't it, or expression. So you could cross multiply if you wanted. Now there are 2 ways to sort of do this question, and either's valid. And one of the things you'll start to learn as you get better at algebra is that there are often many ways to do the same thing. And part of developing a skill is to understand which one is most appropriate for the question you're doing. So let's go option A here. So here we're just going to use cross multiplication. So essentially, we are going to go 9 4x subtract 1 over 2x equals 15 over 1. So we're going to say, first of all, 9 4x take 1 times 1 equals 15 times 2x. So we've cross-multiplied the denominators, okay? Now, we could, if we wanted to, multiply everything out. So 9 4 is 36x, take away 9 equals 30x. Okay, which is the smallest x term? Well, 36x and 30x is that one. So we're going to move this across here, and we're going to move the number term or the constant over there. As you move them, the signs change across the equal sign. So 36x take 30x equals, that becomes a positive 9 now. So we end up with 6x equals 9. So x equals 3 over 2. 9 over 6, 3 over 2, 1.5. Okay. Now, for option B, we're going to follow down here, but then we're going to come across here. So we've got 9, 4x minus 1. Times by 1 doesn't matter, so we'll leave it like that. And that's 30x. Now, instead of multiplying this bracket out, we could recognise that the 9 is multiplying everything else on that side. So we could undo it by dividing by both sides by 9, which would give us 4x minus 1 equals 30 over 9x. Okay? Now, does it help us? Well, let's see. We want the x's on both sides.
Okay, so which is the smallest x? Well, 30 over 9 is less than 4 because 36 over 9 is 4. So this is the smallest x. So we're going to move that way. And we'll move the constant across. So you'd have 4x take away 30 over 9x equals 1. Then to do this, we need to give it a common denominator of 9. So 9 fours are 36. 36x take away 30x equals 1. So what do we have then? We have 6x over 9 equals 1. Okay, and oops, if we wanted to do that, then times by the reciprocal. So to get just x, we times by the reciprocal of the thing. So it's 6/9 times x. If you look at that, you consider that as 6/9 of x. So to get rid of 6/9, you times it by the reciprocal, 9 over 6, because that gives you 1. So we times the other side by 9 over 6 as well. Okay. So that gives us x equals 9 over 6, which x equals 3 over 2. Okay, so this method looks a bit more complicated, and for this case, it isn't the one you'd use, but it demonstrates a slightly different way of doing the equation, okay? And sometimes that method may be useful. Now here's another slightly more complicated equation, okay? It has 3 terms. There are 2 fraction terms on the left-hand side and 1 number on the right-hand side. We could turn it to a fraction by making it 8 over 1 if we wanted to. Now, you could just work on the left-hand side, okay? So you could ignore the right-hand side for a minute, do an addition, so that would be a common denominator of 10, work all that out, and then end up with an a over b equals c over d and cross multiply, okay? However, there is a simpler method, and it relies upon, again, balance. The fact that what you do to one term, you do to all terms in an equation, irrespective of which side they're on. And what we're going to do here is we're going to look at all 3 terms as fractions and find the lowest common denominator. Okay, so the lowest common denominator of 2, 5, and 1 is 10. And then what we're going to do is we're going to times everything, all 3 terms, by 10. Okay, x plus 1 all over 5 equals 10 times 8 over 1. Okay, and now instead of multiplying out, we cancel first. Remember the mantra, simplify before you multiply? So let's do that now. So here we have 10 times a bracket, inviolable term, over 2. So we can cancel these out, 5 and 1. Okay, this one, 2 and 1. This one, the third one, this one doesn't cancel out because it's a 10 and 1 on the bottom. Okay, but what we've done effectively is the denominators are all 1. So we don't need them anymore. Okay, so now we can write, nice and simply, 5, okay, 2x minus 6 plus 2, x plus 1 equals 10 times 8. So the denominators are gone. And denominators are always the hard part anyway. Now we can multiply out. So 10x take away 30 plus 2x plus 2 equals 80. Collect like terms together. So 10x plus 2x, 12x, minus 30 plus 2, minus 28 equals 80. We've only got one x term, so we'll move the number term across and change its sign. So 12x equals 108. So x equals, what does x equal? 9. Because 9 12s are 108. Okay, so this idea of multiplying through an equation by the lowest common denominator is very powerful. Gets rid of denominators and helps simplify the work you're trying to do.
Here we have another example, and probably one of the examples that causes the most mistakes in an algebraic fractions question, okay? We have one algebraic fraction, subtracting another algebraic fraction and giving us an answer, and we have to solve it. Now again, they're just fractions. We just use the same methods as we used in the last example. So, first thing, find the lowest common denominator of the three terms, irrespective of the equal sign, okay? So first off, we know that that's, as a fraction, minus 1 over 1. So the lowest common denominator of 7, 2, and 1 is 14. So we're going to times all of them by 14. So 4x minus 5 over 7, take away 14 over x plus 2 over 2 equals 14 times minus 1 over 1. Okay, so the reason we do this is because, as with the previous example, we can cancel the denominators out. So 14 and 7 for this first one, our common denominator is 7, so our common factor is 7, so there are 2 7s there, 1 7 there. Here, 14 and 2, our lowest common denominator is 2, so there are 7 2s in 14 and 1 2 in 2. And here, 14 and 1, highest common factor is 1, so we don't need to cancel. Okay, so now we can multiply out. So what we end up with first, before we do that, and often it makes sense to do this right out so you can see what's going on, is 7x plus 2 equals 14 times negative 1. So all the denominators we don't have to write because they're all 1. And getting rid of the denominators is one of the key things processing algebraic fraction questions. So now we can multiply everything out. So 8x minus 10. Now, here's the biggest mistake people make, okay? This 7 is not multiplying x plus 2. It is this, negative 7. That's where the biggest mistake is. Loads of people will go 7 times x, 7x, minus 7x, and then go 7 times plus 2 is plus 14. But it's not 7 times plus 2 is plus 14. It's negative 7 times plus 2 is negative 14. So whenever you see algebraic fractions and there's a subtraction, you have to be really careful. Okay? So negative 7 times x, negative 7x, negative 7 times plus 2, negative 14, equals 14 times negative 1, negative 14. And now it's just a case of collecting the terms. So we have an 8x and a negative 7x, which leaves an x. Then we have negative 10, negative 14 is negative 24, equals negative 14. And then we don't want the negative 24 there. Move it across and change its sign. So it becomes x equals negative 14 plus 24, so x equals 10. Again, check it back here. So is 4 times 10 minus 5 over 7 minus 10 plus 2 over 2 equal to negative 1. Well, 4 times 10 is, hang on, let's use this. So 4 times 10 is 40, take away 5 is 35. 35 divided by 7 is 5, so this all comes to 5. 10 plus 2 is 12, divided by 2 is 6. 5 take away 6 is negative 1. So we know that's right. Okay, so minuses, subtractions with algebraic fractions should be very careful. Last example, except for an exam question example, and we have this. Now, to all intents and purposes, this seems quite easy, okay? But this is probably the question type that you'll most get in a higher paper at GCSE, okay? So, first thing we can recognise is if we stick a bracket around there and stick a 1 over there, okay, we have a over b equals c over d. So we can cross multiply, okay? So we can end up with 15 over 1 equals x, 8 minus x. Multiply out, 15 equals 8x minus x squared. Now, as soon as you get to here, you finish processing the algebraic fraction. You have an equation that you should all be able to recognize. Its highest power is a squared power. It's a quadratic equation. So quadratic equations we can only solve, they're equal to 0. So we need to rearrange this so it equals 0. Okay, so as it's a negative x squared, I'm going to move the negative x squared this one that way, and I'm going to move that one that way as well. So move them, we change the sign, so we'd end up with a positive x squared, a negative 8x, and a positive 15 equals 0. And there we have a standard factorizable quadratic. Okay, so it's a is 1, so we can, and there's 3 terms, so we can double bracket it. We know that's x and x. We know that these 2 terms have to equal plus 15 if you multiply them together, and if you sum them, they have to come to negative 8. So factor pairs, well, 1 and 15 doesn't going to get to 8, but 3 and 5 will. So we know the numbers are, or we hope the numbers are 3 and 5. So 3 and 5. We need a positive 15, but a negative, a positive product but a negative sum. So that means that they have to be like that. Then to solve it, each one of these has to equal 0. So x minus 3 equals 0. So x equals 3. Or x minus 5 has to equal 0. So x equals 5. And there are our 2 solutions. Okay. So here we have what's famously known as the Hannah's Sweets problem. It was a problem that appeared in a old-style GCSE exam question that caused a massive furore when kids came out of the exam, and it went viral. So you can Google Hannah's Sweets problem, and you'll see they were all outraged that this was too hard a question. And actually, it's a very simple question. But as normal, it revolved around using some algebraic fractions. Okay, so I'm going to show you how to solve this and where the algebraic fraction skills come in. As always with these sort of questions, the harder ones, the key is the model. It's all about the modelling, taking the words and turning it into a mathematical model, and then the maths itself is easy. And if you've got to this far and understand the 3 videos, you'll know how to do it quite quickly. So if you want, you can have a go yourself before I start showing you. Okay. So let's go. There are n sweets in a bag. So there's an unknown, okay? Now, if you go down to the end, it says how many sweets are in the bag. So if we have an unknown and we need to turn it into a number, make it a known, we're going to have to solve it. So we're going to have to solve it, we need an equation. Now remember, an equation is just a description, okay? It's describing some problem. So the key skill in this question is to turn this into an equation. So n sweets in a bag, 6 of the sweets are orange. So let's say, so we have n sweets, okay, 6 are orange. The rest of the sweets are yellow. So we have some sweets that are yellow. Now we don't know how many there are, so we could use another letter. But if we add another letter, we must be careful, because now we've got 2 letters. You can't solve an equation with 2 letters. And remember, for every variable you have, every unknown, every letter, you need an equation if you're going to solve them simultaneously. So if we add 2 letters, we need 2 equations. So I'm just going to leave it. We'll call it x to start with, but we must be careful with it. Okay, so Hannah takes at random a sweet from the bag. She eats the sweet. So she's taken a sweet at random, so there's an event. Okay. And she's taken a sweet at random and she eats it. So we take 1 sweet. So we're going to end up with, and what does she do? She then takes another sweet at random. So she's going to take 1 sweet out of the bag. That's event 1. And then she's going to take another sweet out of the bag. So subtract sweet 2. Okay. The probability that Hannah eats 2 orange sweets is a third. So we have the probability of orange and orange equals a third. So there we have a number, okay? We know that some probability is going to equal a number. So there is the body, or the skeleton, I suppose, of our equation, okay? Something equals something. So this question, hopefully what you realise, is revolves around working out the probability of orange and orange. And somehow, during that, we're going to find out how many sweets are in the bag. Okay. And how many sweets are in the bag is n. So we need an equation. We've only got one piece of information, one statement, which gives us one equation, okay? Now, we could come up with another equation up here if we wanted. We could say, well, if there are 6 sweet orange in a bag, X are yellow and N is sweets, we could say that 6 plus X equals N. That's a true statement. Then we'd have 2 statements, and we could use that perhaps to solve it simultaneously. But the other thing to realise, if we only have one equation given, and we only want to use one equation, it's N we want, so can we somehow describe the number of sweets, not as a different letter X, but using this first letter N? Well, if you have N sweets, and orange is 6, okay, how many is yellow? Well, you've got N sweets, and 6 of them are orange, so if you take 6 away, the rest must be yellow. Okay, so there we now have 2 descriptions, both using the same letter, okay, or based upon the same letter. So now we can go down to this bit. So probability of orange and orange. Okay, so what's the probability that the first event is orange? Okay, so first event is orange. So how many sweets did it start with? 6 orange sweets of a total number of N sweets. So that must be the probability that our first sweet is orange. Okay, now probability of orange and orange, so we need the second event is orange as well. Now, remember, she eats the sweet, the first sweet, so she doesn't put it back, so we have removed 1 sweet. So the probability of the second sweet being orange, well, there were 6 oranges to start with, but we've eaten an orange sweet in the first event, so now there are 6 minus 1, or 5 orange sweets. How many sweets are in the bag? Well, there were N, but we've taken 1 out because we've eaten it, or Hannah's eaten it. So, N minus 1. Okay, and there we can see our algebraic fractions. So now we have event 1 and event 2, orange and orange. We can take these and put them up here. So the probability of orange and orange is event 1, 6 times N, and is multiply in probability, and probability of the second one being orange, N minus 1. And we know that probability comes to a third. Okay, and here is a standard algebraic fraction question. So the hard part, as you can see, all it's working out was to take all of this information, distill down the key pieces, work out what's going on, create a model for it, turn that model into an equation. Okay, that's the hard part. That's why people struggled with this question. It wasn't the bit that's about to come up. It was that. So hopefully you've managed to follow that. And it's quite common now. They sort of were so happy they'd made this question for an exam. They've used variations on it quite a few times since. So you now know how to do this. Okay, so multiplying, can we simplify across the time sign? Well, no. We've got 6 and 5 as numerators, N and N minus 1 as denominators. So 6 times 5 is 30 over N squared minus N equals a third. If you recognise that that's inviolable, we've got A over B equals C over D, which means we can cross multiply. So we've got 90 equals N squared minus N. Okay, if you don't know how we've done that, we went 30, we moved the denominator 3 diagonally across the equal sign. That way, we had a 1 up there, and we moved the other denominator diagonally across the equal sign. Okay, this is now a standard equation. What type is it? Well, its highest power is a square, so it's a quadratic. It needs to equal 0, so N squared minus N minus 90 equals 0. Solve this. So A is 1. There are 3 terms. I know we can factorise it. If you couldn't factorise it, you'd have to use the formula or completing the square. Okay. You should also realise that there has to be a whole number of sweets in the bag. We'd like to think there's a whole number of sweets in the bag. So that would suggest you could factorise it, because you're going to get an integer answer, or at least one integer answer. Okay, so three-term quadratic. A is 1, we know is going to be n and n. So factor pairs of negative 90, that's sum to negative 1, which is the coefficient of b, coefficient of the n term, okay? So 10 and 9, okay, we need negative 1, so that means the biggest one's got to be negative, the 10, positive there. Always multiply it out in your head just to make sure it's right. So n times n is n squared, plus 9n, take away 10n is negative n, and plus 9 times negative 10 is negative 90. Solve them, so each of the brackets has to equal 0. That's how we do this zero product method. So n plus 9 equals 0, so n equals negative 9. N negative 10 equals 0, so n equals 10. Okay, now next bit, you have to make sure you've got two solutions to the equation, but we're now taking this equation solutions back up into the context, the real world. So we have to account for both of our solutions. So okay, so we can say we discard n equals negative 9 as we can't have a negative number of sweets. Okay, so you must make sure you do that. So therefore, there are 10 sweets in the bag, because that's the question they asked us. Okay, so this is a sort of high-level question you'll get the grade 8s, grade 9s, possibly. Okay, they'll give you a context, load of information. You need to make a model. You'll end up probably having to create an equation because you'll need to solve it to get a number. And then whatever those solution set is, you then apply that back through the model to the context itself. And that's the joy and the power and the pain of algebraic fractions.